All right, so let me tell the people who didn't quite understand last time. Let's try. I'm going to try to slow down. All right, but maybe the people who weren't understanding can nod once in a while, and then I'll move it further again. All right, and so there's some obvious things about computing. We are in computer science after all. You need to be able to talk about computing. And what are we going to do now? We're not going to prove anything. We're just going to translate obvious statements about computing into first order logic statements. Why? So that later in 2001 and in 3101, when you need to prove them, you'll know the language, right? Right? See, I even have the grad course saying they should do these slides, right? All right, so all right, so these are just this is just when I was trying to tell professors who cared, and the truth is nobody did, what I was doing different than George, and I said I'm going to try to cover all of this, and it looks hard to believe, right? But we're not going to prove all these theorems, right? We're going to just talk about it. All right, so Hilbert, right? Well, maybe let's start before Hilbert. Euclid came up with an algorithm, and people say his algorithm was the first algorithm. And, you know, actually, I always say, is that true? Well, I don't know my history. Euclid was a Greek, so it was a long time ago, right? But the pyramids were built before Euclid, weren't they? I mean, pyramids are old. And if they built pyramids, they know how to do math. So how did they do math without algorithms? I don't, you know, they must have had methods of doing them without pinning down what is an algorithm. All right. So Hilbert, I don't know if this is when he was born or when he said his things. I think it was when he was born. He had a conference in Paris, which named, I think, 20 problems, which turned out to be, yes, the big open problems in mathematics, right? It brought Gödel came along, right? Turing came along from it. It was the open problems, right? Here I had Gödel, right? Gödel came and said, all we have is logic, and he proved all these things in logic, right? So that's why, in fact, you might wonder if I'm talking about computing here, why I'm not talking about Turing, because Turing came up with the Turing machine. But, you know, Gödel was before him, and I must admit, I'm more impressed with Gödel. So Gödel did come up with models of computation. They just turned out not to be able to compute everything, but they did pretty damn well, right? All right, so Turing, in fact, and also he's a logic guy, and we're trying to write it down as logic, right? In fact, Gödel, he didn't know about computers, right? In fact, he was trying to prove things about logic, right? So when I say he came up with a model of computation, he did it without thinking about computers. All right, so what do we have? Various objects. One object is a computational problem, right? Sorting is a computational problem, right? What is sorting? It says for every input what the required output is, right? And then we have an input, right? Right. So what the input to sorting is an array of values, right? And what do computer theorists assume it is? We assume it's just a string of bits, right? For theoretical computer scientists, the input's a string of bits. But you can think about it, you can use those bits to encode any object you want, right? This string of bits can be our sequence of integers, right? And then what is P of I? P of I is the required output, right? So in our case, you give sorting a list of numbers and it returns the same number sorted, right? Right, we're just defining our notation. Everybody get this so far? All right. What does computable mean? Computable means that there's an algorithm that can compute it. And what's an algorithm? All right. So Gödel had his definitions of algorithms, though they were all logic based. They weren't computer science based, right? Turing came up with a definition that was computer science based. And you might even say Euclid was the first one to say, hey, here is something I'm going to call an algorithm, right? All right, so what's an algorithm that solves sorting? Insertion sort is an algorithm. And right, if I was a theory person, I'm going to assume it's a Turing machine, right? But it could just be Java code, right? And so then what is A of I? Right? Well, A is an algorithm, I is an input, and oops. So you plug an input into an algorithm, and what does it do? Well, if it works, it gives you the right answer. Right? Everybody buy that? All right. So if algorithm A it computes problem P. All right, anybody want to say, give me a first order logic statement that says A computes P. We have one P. I give you P. P is sorting. I give you one algorithm. I give you one, yeah, for all inputs. Right, right? It gives you the right end, right? So here, what am I saying? I'm saying algorithm A gives me the correct answer for problem P on input I, right? Why? Because the output of A equals the required output on input I, right? So Gödel can just write it down that this is, we have three objects, P, I, and A. And I'm just saying a relation about them, right? I could have the relation solves that takes in P, A, and I and returns true or false, right? This is just the same. You give it three objects, it returns true or false, right? All right, so so now we have to build up a sentence, right? So computational problem P is computable. What does that mean? It means algorithm A computes P, right? What does it mean for algorithm? Which algorithm? Right? There's at least one algorithm, right? Certainly every algorithm doesn't do it. We just have to say there is some algorithm that does it, right? All right, what does compute mean? Well, it gives the right answer on input I, right? Okay, great. But for which input? All inputs, right? Right? It has to work for all inputs. All right. What does solve mean? Right, that. All right, so now we have these various things. I want everybody to think about this, even the people on their phone, right? We want to know, do you say there exists an algorithm for every input? Or we say for every input, there exists an algorithm? How many people are willing to say for every input, there exists an algorithm? Anybody willing to say that? All right, sorry, you're stoned. Not, I mean, we're going to throw rocks at you as opposed to you smoke. Well, maybe you're smoking marijuana this morning. That's possible too. All right, this is bad. This is what drove me to making PowerPoint slides and teaching this course. All right, students in 2001 don't understand this, right? This is saying, you give me an input, and I'll find you an algorithm that works for that input, right? That's not deep, dude. I need to come up with an algorithm that works for your input. Well, I happen to know that your input, the output is 5. So my algorithm, what does it do? It just says 5. Not exciting, right? So, right? You better have an algorithm that works for every input, right? Right, so this is our game, right? Right, so here, let's go through what these things say, right? What does this say? It says, I have 3 objects, and what's the relationship? The relationship is that algorithm A on input I gives the right answer for problem P, right? And then we bring in a for all. What is this saying? It's saying algorithm A solves P, right? I don't have to really talk about I anymore. And what does this say? It says something about P. It says P is computable, right? Everybody good? How does the game go? I want to prove that P is computable, right? These guys are taking 2021-01. And poor Jackie, not poor Jackie, poor them, Jackie gives them some crazy problem. And Jackie says, is it computable? And they have to prove it's computable. How do they prove it's computable? Right? They're invested in proving that it's computable. So what do? They produce the exists. They come up with an algorithm, right? And they have to do it in 20 minutes, right? Absurd. All right. So then, now once they come up with an algorithm, what does Jackie do? Sorry, but Jackie's the adversary, right? He gives their program an arbitrary input. And, right, it's hard. And then what do they do? They run his program on Jackie's input. And ideally it works. 7% of the, I don't know what the average was. 7%, I think. How bad was the average? 30%. What? 30%. 30%? All right. So 30% of the people managed to do this, and 70% didn't, right? So he says, I have an algorithm. I have an input. Does it work? Right? That's the game. We all know this game. It's what we do in computer science. And you note here in this sentence, P is free. Why is it free? It's because it's a statement about P. It's saying P is computable. You plug in sorting, and the answer is yes. You plug in the halting problem, and the answer is no. Right? 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 If P is computable, then the prover can give you an algorithm. Right? Here's referring to the guy looking at his computer. Right? This is what we don't want you to say. right? Because for every input, there's an algorithm that solves the problem. Even if we're talking about the halting problem, right? Halting problem is what? I give you a Java program and an input, and I ask you, does it halt? Well, the answer is either yes or no, right? So I have the program that only says yes and only says no or no, right? For every input, one of those algorithms gives you the right answer, right? Oh, here, this is saying the same thing, right? All right.